So this is partly engineering, and it's partly to convey a frame of mind, a way of looking at problems. I'm a picture person. This is a diagram method. And I'm going to start with some stories. So is this supposed to work? Yes, very good. So the framework or the mental images of a closed chain. And the idea is to try to find a chain or create a chain if you're the designer to understand a complex system and how things interrelate to each other. I am going to have, if I have time, a little bit of application to mechanical assemblies, but I think maybe the stories I'm going to tell are a little better. I've done a lot of reverse engineering, and so have many of you, I'm sure. And part of the problem is to understand how to start. How do you get a handle on what the problem is? And either we have to understand some other person's product because we were consultants, or we had to enter into systematic problem solving. And I'm a system engineer. Mechanical assemblies are systems. They are systems that you can put your hands on. You can't put your hands on the air traffic control system, but you can put your hands on a Luxo lamp, and you can move it around. It's a system, parts that work together to produce some result. And diagramming the relationships is the way to understand how this works. And also, I got into network theory about 10 years ago. And assemblies can be modeled as networks. Every part is represented by a node, and there's a line between two nodes if the parts connect to each other. So diagramming also helps you to understand mechanical assemblies, manufacturing processes, supply chains, the whole works. So this is one of the ones I made. This is a bicycle. Can you tell? Here are the, I'm sorry, the rear wheel, the front wheel, the frame is here, the handlebars are here, the seat and so on is over there. And you can see that some of them are given colors. And in social network theory, they're called communities. And social network theory is full of algorithms for helping you to identify the communities. For us, we'd call them modules or subassemblies, perhaps. And it's context-free. It just says, can I find a bunch of nodes that have more connections to each other than to nodes in some other collection? It's a circular definition, and you have to iterate in order to find out what to do. In network theory, the algorithm by Newman and Girvan is probably about the best one. Doesn't need to know anything about the item in question. Sorry. That's a V8 engine. It only has one of the valve trains. I have all the pistons, I have all the connecting rods, I have all the wrist pins, all of that stuff. Again, an algorithm like the Newman-Girvan algorithm has been used to find all of those communities. Now, what's interesting about this is that it doesn't tell you anything about how the thing works. It's only about what the communities are. And social scientists are fine with that. They can really understand an organization by finding out who talks to each other the most, who's isolated from who else, and so on. It doesn't really do us any good as engineers. What does us good is to find some closed loops. So let me show you one simple loop. This is whoops, sorry. Let's go back. Hello. So here's the air loop. Air comes in, it goes in through the intake manifold, into the cylinder head, out through the exhaust manifold, and out to the outside, and new air is brought in. That's the dashed line. This is the valve timing loop. There actually is a loop. There's a chain that runs. But the chain is just one of those nodes. And it goes from the crankshaft gear, into the chain, into the cam sprocket, into the camshaft, into the valve cams, through the head gasket back into the block. Okay. Here is the main power loop, starts with the block, goes into the main bearings, into the crankshaft, connecting rod, wrist pin, piston, and then through the combustion gas. The dashed line is the combustion gas, into the combustion chamber on the head, through the head gasket, back into the block. And these loops describe the function of the engine. A car engine is an air pump. And the more air you put through, the more power you get out of the engine. And these chains, these links, connect the communities. And so the communities themselves don't tell you how it works. And you can't tell unless you know what an engine is. You have to find those loops, okay? So that's the idea. All right. You don't react to light. You don't react to whatever. There's going to be a talk on perceived quality. This is a clip from an advertisement from Lexus from about 1992. Changed the car industry forever. A shiny ball bearing rolling down the groove between the hood and the fender. And it says right there, if we took care of this, you can be confident that we took care of the other stuff that you can't see. And this changed the car industry forever, and they got interested in fit and finish, how the parts mate to each other, all led by the Japanese. A good deal of robust design involved in this as well, but perceived quality is really the clue. So the next three examples that I'm going to give you is student work, and I hope I got the student's name on there someplace else. At any rate, the car company is starting up production of a new model, and they can't get the hood aligned to the front fenders to their satisfaction, and they can't figure out what's wrong, and they can't figure out how to start, okay? And what I did was to ask two students, one located at the car company and one located at a supplier that purportedly made all of the sheet metal parts that go into this. I had a friend at Cranfield a number of years ago, and he had a contract with British Aerospace to look down the supply chain and find out how they were doing in design for manufacturing. And he said, fine, give me a list of your suppliers and I'll go talk to them. And that was the end of the project. And it turned into a project to find the supply chain. And it took him about a year. People don't know who their suppliers are, okay? So this is the diagram. And it's got on here where are we? It's so tiny. The hood and the front fender. And I have drawn two red lines there, and that's my symbol for what is commonly called the key characteristic, which is terminology I got from Boeing about 25 years ago. They mean something completely different. And it's a summary of a very complex relationship, obviously. But that's an assembly level dimension that we want to keep. That's where the ball bearing was rolling. Those two parts do not assemble to each other directly. A assembles to B, which assembles to C, which assembles to D, which assembles to E, which finally assembles to the other one. The hood to the cowl top to the firewall, the inner fenders to the firewall, the radiator support separates the inner fenders and puts them to the right spacing, and then the outer fenders to the inner fenders, and that completes the loop. And it passes through a number of parts, a number of fixtures. All of these come from different companies, okay? And in a meeting, our full-service supplier said, oh, we buy the radiator support. Okay. So here's the final chain. It took the students a month to draw this. Nobody at the factory could draw that picture. Now, you can't diagnose this problem if you don't know what the pieces are and how they relate to each other. And this took work. Here's the next one. Again, a door, a piece of metal that swings. Part of the engine housing. I'll show you a picture in a minute. Several suppliers make parts. Whoops, there it is. So when the door doesn't fit at final assembly, the maker of another assembly, the inlet, is blamed, and they don't know what's wrong. Finally, the diagram is made, and we go down the diagram and find that there's uncoordinated datums and a misdesigned assembly process. And a non-locator surface was used as a locator. And this was the root cause. This thing is big, as you can see. Here's the diagram. Tim drew this diagram. He was stationed at Vought Aircraft, and they make this inlet. Pratt & Whitney makes the engine. McDonnell Douglas in St. Louis makes the pylon. The accessory door is made by another branch of Vought. Final assembly is done at another branch of McDonnell Douglas. And this is the simple version of the diagram. This is the complete version of the diagram. Here's our key characteristic. You have to make this joint very well. It's aerodynamic. It isn't for appearance. It's important to the efficiency of the engine. You can maybe see that there are 13 links in this chain. Anybody who designs a chain with 13 links needs to have his head examined. Okay? 5, 6, maybe, that's okay. You get up to 13, you're in serious trouble. And what Tim was able to find out was that this inlet was being built face down. And it was indexed off of this lip. This is an aerodynamic surface. It is not a mechanical locating surface. The mechanical locating surface should have been the ring back here where it joins to the engine. And that would have meant hanging the thing as you built it. And why they didn't want to build it the other way, we don't know. All of this is lost in the mist of history. And one of the things I'm interested in is not only understanding design intent, but how to document design intent. And if somebody draws this chain, at least we can tell, sorry, well, you work going backwards, but not for, hello. But presenting this chain so that somebody can come along later and say, well, that's what he wanted to do. And why isn't it working? Well, maybe it's a bad chain. Maybe it wasn't implemented properly. We'll find out. One of the things you don't want to do is look for a single place where it's wrong. Very few problems have single causes. If you want to write that one down. Very few problems have single causes. And when you have 13 elements in the chain, you have many, many opportunities for problems to arise. Here's the third one. This was Mike Rutz's master's thesis. All these are great theses because the student did the work at the company. He's not sitting back at MIT trying to figure out what's going on. But that's the way to do a thesis of this type. You put the student out there for 3 months or 6 months, long enough to absorb the problem. So here, again, an outgrowth of this ad from Lexus. Companies arose that built what are called optical coordinate measuring machines. And these are sets of lasers, and you measure car bodies for their accuracy. And the student was sent to a particular factory at a company that had 10 or 12 of these factories. And the coordinate measuring machines worked at every plant except this one. And the student was sent there to find out why it didn't work. It would run for a day or two, and then it would stop. And then it wouldn't get fixed for 2 or 3 days. And I said the same thing to him again. Go draw the diagram. Okay? I went to the factory. I asked for the contract to look at the specification. There was no top-level spec. There was no spec that said this system shall be able to measure car bodies within X millimeters. The highest thing in the spec was the camera will have resolution of X millimeter. There was no top-level spec. Why was there no top-level spec? Because the car company insisted on reusing one piece of its old equipment. And the vendor of the system said, that's it, we will not guarantee the system. Okay? And that's why there was no top-level spec. Turning over the rocks. Well, that principle number 1 is to turn over the rocks. Okay? Let's go back. Boy, I really lost a lot of them. Turn over the rocks. Keep turning over the rocks until you don't find any new worms. Okay? You keep finding worms that you found before. Then you know you've reached some kind of a steady state. So one worm after another. Coordinating trades, reuse of old equipment, lack of system awareness, multiple reporting paths in the organization. These problems are never purely technical. There are three general aspects: the technical, the organizational, and the managerial. And if you don't look for all three of these aspects, you're not going to solve the problem. You can't just have good parts, okay? They can be messed up anywhere else along the line. Hello? So here's Mike's diagram of the system. It's the car body here. This is the conveyor. This is the lifter. The lifter was what the company wanted to reuse. These represent the different cameras. And what we found, it's the same is true with all of the other ones, the different links in the chain have different owners. And this is, again, a sign of trouble. The different owners don't know each other, they don't like each other, they don't know that they're sharing this chain. You outsource pieces of the system somewhere else, they have no idea how it fits into any coherent whole. So we have the vendor of the measuring system, we have the conveyor vendor, we have the car maker as the owner of the existing lifter, we have the car maker as manufacturer of the car body. And then, maybe I've skipped a slide. Anyway, here's the chain. And there's 7 or 8 steps in this chain, and I'm representing here symbolically one of these key characteristics. It's the ability of the system to measure. Okay? This key characteristic is not a property of the car body. It's a property of the system. Can the system make the measurement? This is pretty sophisticated for a student to put together a diagram like this. So what we found when we asked then who owns what pieces of the chain inside the factory, 3 different trades: the welders, the tool makers, the inspectors, and that's when the system was working. As soon as the system broke, new owners came along, except that they were only available on the night shift. And so now you have shift coordination, where the day people don't tell the night people what's going on. The night people won't listen. They aren't available. You can't tell what's going on, yada, yada, yada. So this was kind of interesting. And the other thing was that the reporting paths were different. I sent him to another factory at the same company whose measuring machines work just fine. Tell me what's different between the 2 factories. They had a different union contract. They had fewer trades involved. The reporting paths converged at some place below the plant manager, whereas at the other plant, the reporting paths didn't converge until you got to the plant manager. And nobody can get an appointment with the plant manager. He's too busy. So you can't get any decisions. So part of the analysis of any such problem is to understand the reporting paths. And I had a very good student in another situation, and he found that there were 3 reporting paths, and they each ended up at a different vice president. Okay? This had to do with car doors: closing effort, wind noise, water leakage, and fit and finish. And each of these were basically a lobbying organization for their attribute. No, fit and finish is better. No, closing effort is better. No, wind and water leakage is better. It was a mess. All right, so the broader context. I've said a lot of this stuff, and I worked ahead in case I ran out of time. So we have the managerial, the organizational, and the technical. Roles and responsibilities and incentives. Incentives are a terrible trap. People will do what's necessary to get their score up according to the incentive. They don't care what it does, and nobody can predict. Organizational: lines of command, communication, assign of tasks, mustering of expertise, and so on. Technical: what engineers think about. It's the last thing. If you don't have the managerial right, you can't get the organizational right. If you don't get the organizational right, you can't get the engineering right. So we're looking for these functional loops that link the communities. So what are the steps? Identify the problem in terms of a missing capability at a high level, or if it's a mechanical assembly, an assembly level dimension that you want to control. Then you have to find the elements that support correct behavior. Parts, people, organizations inside the company, suppliers outside the company. You have to identify all of them. This can take a lot of work, and again, don't assume that there's only one faulty item. I was at one company, they were very deep into Six Sigma, and a student of ours did a survey just on car door problems and found that out of 1,500 or more that he was able to find in the database, every single one of them came up with a single cause. And he said, this is impossible. It cannot be that you can find a single cause. And this company was single cause focused. That was their culture. There is a single cause, we will find it. And they were able to solve some fraction of their problems, but not all. Identify the links, the contracts, the specifications, the CAD models. Formalize these into a chain of nodes and links. What you find inside typical mechanical assemblies is that there are many key dimensions that have to be held. And they are each supported by a chain. And when you count up the typical chain having 6 elements in it, the typical assembly having 9 or 10 parts, typical assembly having maybe 2 or 3 of these dimensions, you cannot avoid having parts be members of more than one chain. And this is part of the problem with axiomatic design, where you can't make the separation. You will get a kludge, you will get a Rube Goldberg or a Heath Robinson, because you're trying to use a single part for a single function, and you cannot do that. And so you're going to have these interlockings, and that's what one of the papers that Thomas talked about. I haven't read it, but I'm guessing that this notion of interaction, it has to be managed. There are going to be interactions. These things cannot be separated from each other. Hello? Step 2, identify the owners of the links and the nodes. Identify the key relationships that must exist in order for the chain to function correctly, especially if it's not functioning correctly. Find out what's wrong at an interrelationship level. The problems are often going to occur at the interrelationship level, on the links between the nodes. Not necessarily on the nodes, but don't rule it out. It could be the nodes. Try to fix the situation at the lowest practical level and elevate it if it doesn't work. This statement here is the mushiest. Okay, that says get smart and solve the problem. But you're equipped, okay? You're equipped with knowledge, with a way of thinking about the problem. It's a chain, okay? It has multiple owners. We have to find the chain. Nobody will be able to tell us what the chain is. Nobody has ever thought of it as a chain. But this equips you to think about the problem. And that's why I said at the beginning of the talk, it's about a way of thinking. So applied to mechanical assemblies, as a conceptual design level, think up what it looks like starting from customer needs down to specifications, then down to the key dimensions at the assembly level that you need to hold. There's that step in product development. You always start with customer needs, then you go to specifications, and then you go to these key dimensions if it's a mechanical assembly. And we call these key characteristics. Anna Thornton gave a talk a few years ago about this sort of thing, managing the key characteristics. Draw the chain of parts and the fixtures. There are often fixtures. For this car hood, there were fixtures. You can't put sheet metal parts together normally. They have lap joints. And so you have to add the missing constraint with fixtures. List all of the coordinate directions in the key characteristic that need to be delivered. In the case of the car hood, really it's all 6 degrees of freedom. But there are situations might just be the X direction, or it might just be the Y direction. In a valve train, you have a spacing between the cam lobe and the top of the valve. This is a single dimension. It's just the axial direction along the valve stem. Consider and verify how each part in the chain is located relative to the others. Location is about constraint, about kinematic design. So a piece of this is about how the parts locate to each other. The parts act as fixtures for each other. The parts convey location to each other. Then you have to establish a common datum structure. I know of problems where the problem turned out that the datums weren't coordinated. The supplier chose his own datums in order to get the parts to fit properly inside his equipment. Identify the dimensions inside each part that carry the chain. The chain enters the part at one locator surface and goes out of the part at some other locator surface and enters the next part. And those two locator surfaces must be located properly with respect to each other inside the part. That's what you do with GD&T or with tolerancing generally, is to locate those surfaces, because the location is going to enter the part here and leave the part there. Each part fixtures the other part at the neighboring point where they locate each other. And so if the X direction is what we have to control at the assembly level, then we have to go around the chain and see that the X direction is controlled at each of the interfaces around the chain. And then we have to critique it. We have to make sure that it's properly constrained if we possibly can, make sure it supports that creation of that segment of the chain. Make a quick check of tolerance capability. I find that people don't know what's going to happen. So just make the assumption that it's root sum square. And just make the assumption that there are 6 elements in the chain to start with. The square root of 6 is 2.5. Now say, well, let's say we can reasonably expect the parts to be within plus or minus 1/10 of a millimeter. Can your system live with 1/4 of a millimeter variation? This particular example has to do with force. Force is the outcome of dimension in this particular assembly. Plugging a connector into a socket. And you have to compress the springs in order to get electrical contact. And the harder you press, the lower the contact resistance is, and the harder it is to insert the connector. So this particular design ended up with, when you include the stiffness of the spring, the square root of 6 times 8.8 newtons per 1/10 of a millimeter to 21 newtons of variation, and the whole range was 2 to 40. This is not a robust design. Half your allowed range is just in the variation, and it's only 1/10 of a millimeter at each place. And the problem is the stiffness of the spring. It was a very, very highly sensitive design. And this was work I did about a year or two. I work part-time. I look like I'm old, but I'm still happy working. Here we go. So I talked about design intent. The key characteristic is a level of the design intent. This is our goal, is to make this key characteristic. Okay? What it is, why it matters, what performance it supports. Okay? Sorry, I went back 2. Identify the chain that delivers the KC, how these parts locate to each other. Your datum surfaces, your coordinate lines, estimate of the sensitivities. So last slide. I guess I'm pretty much on time. Functions at many levels arise from proper operation of closed chains. And these chains are things, people, and organizations. And proper operation depends on defining and implementing these chains systematically. Failures and breakdowns can be diagnosed by analyzing, or if necessary, discovering the chains. In many cases, you're going to have to discover the chain. And the chains span managerial, organizational, and technical domains. What I would like to see in mechanical design is that part of the design is this chain. Put the chain on the top drawing. Make the chain part of the design review process. What is your key characteristic? What is your chain for delivering that key characteristic? Have that question come up at every design review. Do you know what you're doing? When you get done, you have the design intent documented. and it's been scrutinized, it's been critiqued by other people in the design review. If something goes wrong, at least you know where to start. In some cases where you have products that are derivatives of each other, where you're carrying over items from one generation of the product to the next, the people who designed the original one could be fired, retired, or expired, as we said. And you don't know anymore. You don't have anything. He did it, but you don't know why. And this comes up again and again and again. I've done this for 40 years. People do not know why. They may know what, but they don't know why. And we have to reconstruct it. That's what this reverse engineering stuff is about. So to me, design intent for mechanical assemblies is documented in this chain, and saying what the locating surfaces are, what dimensions they have to control, what is the top level dimension that we're trying to control, why is it important, so on and so forth. And if that could be systematized and institutionalized into the design process, you would have better designs, you would have a better way of critiquing them, you would have the documentation, you'd be able to find out what's wrong, or at least you'd be able to start. You would at least know where to look and what the person was trying to do when he designed the thing in the first place. So I'm on budget. I've gone through all my slides. So thank you very much.
So thank you very much for this inspiring talk. I have thousands of questions, but I guess a number of other people as well. And there's certainly room for some questions. I guess Janusz excuses, especially with regard to this topic. A couple of minutes. Are there any questions?
I like your idea of visualizing the key characteristics with the symbol, the double line there. What's your experience? Now we saw this just for one key characteristic. What's your experience when you have to map a complete product with maybe 50 or 100 key characteristics?
Well, it gets crazy. First of all, you have to see if they all deserve to be key characteristics. This is one of the points that Anna Thornton made a few years ago. A key characteristic is something that's important for one reason or another, for function, for regulatory, for safety. That's number one. And number two, that it's at risk due to variation because of variation in manufacturing or assembly. If it's not important, it's not a key characteristic. If it's not at risk, it's not a key characteristic. So first of all, see if all of them deserve to be key characteristics. Then try to partition them, try to separate them. If they're all snarled together, you may have a bad design. And it may be one of the ways of critiquing the design. Do we have the best design we could have? It's unavoidable, as I said before, that these chains are going to share parts, that more than one chain is going to pass through some of the parts. And those parts become very critical. And we call this coupling. Coupling can be benign in the sense that you have enough degrees of freedom to adjust independently. Otherwise, it's called conflict, in which you don't have enough degrees of freedom to adjust independently. With car doors, closing effort and water leakage are in conflict. The tighter the seal, the better the water leakage, the harder it is to close the door. And nobody's ever figured out how to solve that. It's just inherent. And there shouldn't be fights because it's nobody's fault. It's mathematical. You can prove mathematically that it's going to happen. And so the best you can do is reduce the number of key characteristics as much as you can, and then try to separate them to the degree that you can. Not much of an answer, but designing complex things is tough. I go to Boeing all the time. You can't believe an airplane. You can't believe it works at the end of the line, but it does. They all work. You turn the switch and they all take off, every single one of them. And it's like an anthill. The ants get it done, but there is no ant that's running it. There's no 10 or 20 ants that are running it. And I don't know how they did it, but they do it. You can walk the whole length of a car assembly line in an hour or two. You can encompass all the steps to assemble the car. You cannot do that with an airplane. There's 7 million parts.
Another question for you.
Yeah. Thanks, Dan. Very nice talk. You have a lot of experience from consultancy. I guess you go in and you find problems, and I guess you're also able to explain the problems, and a lot of
sometimes, yes.
A lot of people, technical stuff involved. But what's your experience from trying to train these things to organizations? Where do you start? There's a lot of people involved. How does it go? What's the reactions? Is it possible? So on.
Yeah. Well, I wrote a book about it. There's a book. It's called Mechanical Assemblies. You type in Mechanical Assemblies, Whitney, into Amazon, the book will come up. All the copies that were printed have been sold, but they will print you one. They know how to print a single book for a reasonable price. It's quite wonderful. And so you can get this book if you want. It took me an entire semester to teach this to MIT graduate students. I can compress the design part of it into about an intensive week. But you start with the notion of the key characteristic and the network diagram, and then you proceed to explain the notion of constraint and locators.
But I mean, how do you do it in a company? Where do you start if you want to teach the whole organization in a company that they are part of the problem as well as the technical stuff, and you need to involve all the departments and suppliers?
I can't tell you that. What I can tell you is that I have stood up in front of groups of engineers and explained the methodology as best I can, as best I understand it. And I do know, in one case, I got very definite feedback from the vice president. And he says, I go around the office now, and each of my engineers has their chain pinned up to their wall. And they say, this is wonderful. I look at my Pro E, and I can't see a thing. I have no idea what's going on. Everything is coming at me in every direction. This is a very simple diagram. It's just dots and lines. And on the lines, I've got the number of degrees of freedom, or the specific degrees of freedom that are constrained along that line. And the simplification, your ability to see inside what's going on, is an attraction, okay? But how to get people to do it?
But so if one person at the company is responsible for a key characteristic, that's where to start from.
Every process change has to have a champion. And the champion has to push and push and push. Making it part of the design review process, I think, might be a way. That you just don't get your signature until you've done this. Part of the quality management within the company. Every company has a different culture. And I would have to depend on people inside the company who know the company. What is the way to make change happen? There are organizational change experts, organizational behavior experts. I'm not one. And so I really can't answer the question, but it's a very important question, because you can't depend on there being one person in the corner sitting on a stool with a hat on his head to do all this. Everybody has to be able to do this themselves. So it's a great question, and I would put it back to the people who are from the companies, that they think about this or give me their feedback. How do they think it would work in their companies? Really, really an important question.
Thank you very much. I think we slowly need to proceed.
Okay, great. Thank you.
Take that as a last comment towards industry as well, how to implement that. Thanks for your talk. Small gift representing exactly the complexity that you mentioned so often and the dependencies. Thanks a lot.